What is the purpose of oil in a refrigeration system? Well, we all know it lubricates the compressor internal mechanical components and cools the electrical windings of our compressor motor. Oil is thrown from the compressor discharge, risking the following issues: a lack of oil in the compressor, which could then impair the compressor's lifespan, affect its longevity, can get stuck in far-reaching parts of the systems, as we well know. And we know that oil and refrigerant don't just act in isolation, they mix together. And this can affect the quality, the thermophysical and thermodynamic properties of both fluids.
Welcome everyone. Welcome to CO2 Experts Live. So excited about this. I know many of you have been reaching out and asking, when is CO2 Monday going to start up again? When are we going to do some CO2 talk? So this is it. We're launching today, CO2 Experts, and I'm super excited about this session. We got a lineup. It's a huge lineup with the top experts from around the world. And we're kicking it off with my good friend, Nabil Cook. This guy is a rock star in CO2. He's taught me so much. We've just finished a 12-week design course back in the summer with 11 or 12 different people from 7 different countries, and it was a game changer for them. Still getting response back of some of them that leveled up in their position. They got new jobs and they got pay raises. This is awesome. And I learned so much from that design course that I wanted to kick CO2 Experts live off with him, diving into oil management design. I'm super excited about this. Please, if you have any questions, throw it in the chat, because this is where we learn. Ask those questions, because Nabil is the expert. And I'm telling you, when I mean an expert, he can talk about things that just blow my mind. And I know a lot about CO2. So super excited. Nabil, welcome to CO2 Experts. How you doing, brother?
Thanks, Trevor. I'm doing really good. That's the most generous introduction ever. I really appreciate it.
Oh, dude.
You're technical
a rock star,
director
man.
at Amiga Solutions. We specialize in net zero, particularly with regards to refrigeration, air conditioning, and heat pumps. And we predominantly serve the food retail sector, but not exclusively.
Yeah. And it's awesome. We had a partnership for a couple years with James and I, and now we're running the CO2 design courses. So any of you interested, we're launching another one next week. It's to start off the fundamentals of CO2 design. So if you want to learn to become the best CO2 designer out there, or a top one at your company, look into it, book a call with me. I'll throw it in the chat in a little bit. But it's a game-changing program. So today, Nabil, we're going to be diving into CO2 oil design, oil management. We know this is one of the things that a lot of people struggle with. Designers, technicians, sales, everybody kind of struggles with oil management because they don't spend a lot of time or all the time with it. Do you want to blow? There you go. Beautiful. So hopefully everyone can take a look at the screen. If you're listening on the podcast, go over to the YouTube channel and watch it there. So Nabil, I'll let you kick it off, brother.
Thank you very much. So welcome to oil management systems with a specific interest in transcritical CO2 refrigeration. So what is the purpose of oil in a refrigeration system? Well, we all know it lubricates the compressor internal mechanical components and cools the electrical windings of our compressor motor. So oil is thrown from the compressor discharge, risking the following issues: a lack of oil in the compressor, which could then impair the compressor's lifespan, affect its longevity, can get stuck in far-reaching parts of the systems, as we well know. And we know that oil and refrigerant don't just act in isolation, they mix together. And this can affect the quality, the thermophysical and thermodynamic properties of both fluids. So what do we have in a typical oil management system? Following our compressors, we've got an oil separator, number one. We then have an oil filter to keep debris and other impurities out of our oil. Number three, we may have a solenoid valve. Number four, we've then got an oil reservoir. Number five, an oil header. And number six, oil regulators on our compressors to get the oil back in at the right rate and at the right time where needed. So Let's have a look at the oil separator first. As its name suggests, it separates oil from the refrigerant. It's placed at the compressor outlet. In two-level systems, it's placed at the outlet of the higher level, the medium temperature rack, not the low temperature rack. So these days, we've got very high efficient separators, leading to less oil carryover into the rest of the system. Some oil always leaves the compressor, and therefore other components are needed to manage oil in the system. So what we have here is an image of a coalescent cartridge, and you can see a perforated cylindrical bit of metal with perforated holes in it. So moving on, we've got the oil reservoir and receiver. So this is a buffer. It caters for oil circulating fluctuations at different operating conditions. It's sized as a function of displacement, along with the internal volume of the system. So we have a wide range of transitory operating conditions in terms of part loads, part ambience, part saturated conditions, and therefore that's why we need a buffer in terms of oil. It's sized according to the volume of oil that's expected to be contained within the entire fridge system. This could be pipework, heat exchangers such as evaporators, condensers, whether they're coils, plates, vessels, whatever they are, and compressor bodies. It cannot account for poor design of pipework or a poorly maintained system. So on the right here, we've got an oil management system, courtesy of an ARNEG CO2 system. And as you can see there, we've got two oil separators in parallel. Moving on, we've got an oil check valve, equalizer valve, or degassing line. This keeps the pressure in the oil reservoir in check, stops it getting too high, ensures an even supply of oil to the compressor regulators, connects the oil reservoir to the suction line of the compressors. So oil reaches the reservoir with refrigerant gas. What we want to do is try and take out as much of that gas as we can. It discharges that excess vapor into the suction line of the compressor instead of it muddying the oil on the way into the oil sump. So oil crankcase heaters keeps the oil within the compressor body or crankcase at a temperature high enough for suitable operation. We don't want it to be too frigid because it doesn't flow well. It doesn't do what it needs to do. So compressor manufacturers recommend that heaters are operational when compressors are off. And Copeland indeed stipulate that the crankcase heater should be operational for 12 hours before starting the compressor for the first time to prevent flooded starts.
Yeah.
Oil regulator.
Just before we jump in that, other manufacturers are going to do different things as well. You know, this is stuff that you need to dive into and look at those manuals, because Bitzer, I think it says 95 Celsius. They want that oil, you know, so it's not even a time. So some people will do time, some people will do temperature. You got to get into those manuals if you want to learn this stuff. That's why Nabil knows this stuff. He's getting into the manuals and reading that stuff. You go, Nabil.
Absolutely. And then not every manufacturer uses the same metrics to determine whether something's okay. So, for instance, I've looked at plate heat exchanger performance. Some look at velocity only, some look at velocity plus shear stress. So don't just presume that because one manufacturer judges it on this, that all will judge on that same basis, because that's not necessarily the case. So oil regulators regulate oil feeding into the compressor housing. So they compensate for different oil returns in different compressors, maybe different sizes, different displacements, and different usage patterns of the compressor. So it requires a pressure differential to feed into the body. And that delta P or differential is the reservoir pressure minus the suction pressure. So where oil is discharged from the compressor faster than it can be refilled through the regulator, the oil differential pressure must be increased. So typical differential pressure values we see are 1.5 bar, 3.5 bar, and 5 bar differentials. So our photo on the right here is an Emerson oil regulator for transcritical CO2 scroll compressors. Moving on to the oil cooler. Certain systems have got very high refrigerant discharge temperatures and therefore very high oil temperatures. What we don't want to always do is chuck that very hot oil straight back into the suction, because it won't cool the windings. If anything, it will heat the compressor up, cause more degradation, reduce efficiencies, and just shorten the life of the compressor. So we want to cool that oil before sending it back. Several methods for cooling: natural convection, And you can see there we've got a natural convection coil. There are no fans on that. It's just in open air doing its job. Forced convection, dependent on ambient temperature as well. And mechanically cooled, as in that oil is cooled by a separate and dedicated refrigeration system. So mechanical cooling circuits can use separate fridge systems feeding through a heat exchanger. So we typically like to see oil temperatures in the range 50 to 70 on transcritical CO2. That's Celsius, dependent on ambient temperature. So here we've got an Icentra transcritical CO2 system using the Copeland transcritical scrolls, the DVI mid-port, and the exposed oil cooler assembly that you can see there.
And so those oil lines that we've seen there, Nabil, those ones have to be designed specifically for the right size and the length. Is that correct? Because you can't just go and say, okay, I'm going to do 100 loops, 200 loops. It's specifically designed for that amount of loops. Is that correct?
That's absolutely right. It's designed to take at least 50 degrees out of the temperature of that oil. That's a significant amount. So typical discharge temps, about 120 off of those scrolls, especially in higher ambient conditions. Hence why you're seeing that range of target 50 to 70. So, yeah. And obviously it's sized accordingly. It's a natural convection thing. People cleverer than I will be able to do hand counts to select a coil arrangement like that. Some people use software. Right. Some people just have a good feel in their head for how many passes are needed and what the closeness of those passes should be.
Awesome. Love it.
So managing oil throw, don't presume that all compressor types throw oil in the same quantities or proportions. They absolutely don't. I'm not going to go into too much detail on this, but this is an example based on those Copeland transcritical scrolls. Now, this is based on the third generation of those. That may have changed since and moved on, and I must say that, as it wouldn't be fair on Copeland for me to presume that things are the same. They may have changed since. They may have got better. First thing is these transcritical scrolls with DVI mid-port don't use POE. They use PAG oil instead. The next
why is that important? Why is that important to do that, Nabil? Going from what everybody uses, POE 85 or 68, going to the different oil.
It's important with these because they operate at a higher temperature. Higher discharge temperatures consistently, not just at peak compression ratios, but across the full seasonal range of compression ratios. These have at least 10K extra of discharge temperature, and it was found that PAG was optimal for them because of that higher temperature range than POE.
So don't go in and just put any oils in, mixing oils. This is designed by the manufacturers, because I've seen it time and time again, mixing different oils run into issues on sensors, and lubrication. So very, very important. So thank you, Nabil.
No, absolutely. So this is now the real important bit. Research suggests that these scroll compressors required an oil throw that's over 3 times that of the equivalent semi-hermetic reciprocating compressors at peak design conditions. That's going to affect your oil separator sizing, reservoir, oil lines, everything. This is why I do not treat all compressors based on their displacement. Different technologies have different oil requirements. Remember that.
That's so important. That's because I didn't know that. Like, oh, it's a semi-hermetic, it has 6 cylinders. This Dorin, Bitzer, Bach, Copeland, they're doing the same, but it's not. You want to dive into a little bit of difference, how they are different? Like, what are the things? It's the bore, it's the cylinders, the rings. It's about the design. Do you want to just dive into what causes that a little bit from the different manufacturers?
It really depends on whether it's a positive displacement compressor, whether it's rotational. So when we're dealing with a recip, we've got pistons that move back and forth just like a car engine, for instance. When we're dealing with scrolls, we've got a fixed vane and a rotating vane that are constantly meshing in and out of one another. And I think that's the reason that the oil flow requirements are so different. because you're just dealing with a completely different mechanism. That's as much as I can explain it, Trevor.
No, it's perfect. Right?
Yeah. So moving on, we've got oil management system strategies. Now, most of us are used to the strategy on the left, which is to have a single separator for multiple compressors. When we're dealing with large systems, and I mean really large systems such as ammonia in distribution centers with massive open drive screw compressors, we are more likely to have a dedicated separator for each compressor, therefore a multi-separator system.
And I've seen both out there.
Yeah, so have I in my time. Predominantly with the commercial food retail that I deal with here in the UK, it's generally the single separator systems, but I have seen examples of both.
Yeah, same here. So mostly on the commercial supermarket style ones, single separator, getting up into more industrial one, seeing, one separator for 2 compressors, and you have 8 compressors on there, maybe on the rack. So it all depends on the manufacturer and what they're trying to accomplish.
Absolutely. Usually the large ammonia open drive compressors that I mentioned are delivered as a skid with several of those components integrated. The oil separator is on the compressor skid, and many other ancillary items are also on that skid. So it's a difference in scale, it's a difference in market and application. So moving on to oil concentrations, oil is always carried over into the rest of the system, even if an oil separator is installed. So to ensure continuous lubrication of the compressor, the oil has to be returned. Accumulation is not good. The solubility of oil in the refrigerant decreases with temperature, whereas the viscosity and density both increase. Therefore, the evaporator is critical because it's the absolute coldest point of the system, and the oil must be carried out of the evaporator as droplets by the exiting refrigerant vapor. For normal concentrations, which we define as less than 3% volume on volume of oil inside the evaporator, the heat transfer coefficients will not be affected significantly. And actually, there's some research evidence that a small oil film actually affects heat transfer positively. However, if oil accumulates beyond 3% volume on volume, that thickening oil film will act as an insulating layer, and the evaporator efficiency could be noticeably reduced. So how do we go about sizing oil separators? Well, usually these charts are provided by manufacturers of these components. They may have selection software. Just to give an example, Danfoss Cool Selector 2, for instance. Sizes are based on suction temperature of the refrigerant, the gas cooler outlet temperature, superheat and subcooling values for the application, and the cooling or heating duty of the system, whether that be in tons refrigerant, BTU per hour, kilowatts, whatever. The model chosen must have a connection size equal to or larger than the discharge pipe feeding the separator. And we've got some examples of these oil separator selection charts on the right-hand side here for transcritical CO2 refrigeration. So we've got temperature, we've got different connection sizes, and we've got tons of refrigeration within the table itself at a given gas cooler outlet temperature, and superheat and subcooling figures. So how would we go about calculating the size of a required oil reservoir and the system oil charge over oil? So you need to know something about the volumes of the systems, the internal volumes. So there are 3 main contributors to this. There's the actual volume of the oil return line and manifold. There's the oil charge of the compressors as well, and that should be listed in the compressor manufacturer's information on their data sheets, within their software, in their manuals, etc. Finally, there's the oil carryover volume into the rest of the system. So the system pipework and heat exchanger internal volumes. So if we've got no oil separator, presume we've got a 3% by volume concentration of oil in the remaining system internal volume. If we've got an oil separator, it's a lot less. Presume it's 1% by volume in the remaining internal volume. So what do we do with all of that? We add it together. To get the required reservoir capacity, we add the oil return line and manifold volume to the compressor oil volume, to that system carryover volume, and then we multiply by a safety factor, say, of 25 to 50%. So once we've got that reservoir in there, what's the total system volume charge of oil? Well, it will be the system volume before we added the reservoir plus 80% of the reservoir's volumetric capacity. So that's how we work out what total system volume of oil is.
And the big thing is some of the things that I'm seeing now, there are CO2 systems out there that don't even use oil separator or oil reservoirs out there. So you're going to see different systems depending on the application. You may not need a reservoir or a separator. So think about your design, and when you're designing a system, how do you reduce complexity, and how do you make sure that those compressors continue to stay lubricated?
There are examples of that. So there are some systems out there in the field that are using the vessel as the oil capture equipment.
Yeah.
So there's a knowledge based on density difference of where the oil will be in the vessel, and it can be tapped off that port and transported back.
Yeah. So
I've not seen a lot of it, but I have seen an example.
Yeah. And using natural gravity for it.
Yep. Yeah.
Using gravity.
Absolutely. Yeah.
So it's out there. So when you come across it, learn about more of it and try to get more. This is what it's all about. This is why we're here sharing this knowledge with all of you, trying to help you grow your knowledge. So if you learn about it, share that with somebody else, because these are the things that are going to help you get better at CO2 refrigeration.
Absolutely. Nothing ever stays the same for long. Yeah. Oil line sizing. Right. So this is an important one. Take the compressor displacement and multiply it by that volumetric oil retention percentage to get the oil volumetric flow rate. So multiply that oil volumetric flow rate by the oil density to get the oil mass flow rate, and then work on a given line with a given pressure differential from high to low. So for instance, oil separator to oil reservoir, or oil reservoir to MT compressors, or oil reservoir to parallel compressors, and set the line length and use an iterative pressure drop calculation to determine the required pipe diameter based on the inlet pressure and desired pressure differential. So the density and viscosity of the oil refrigerant mixture are required for these calculations. So I'll say that again. Take the compressor displacement, multiply it by the volumetric oil retention percentage, and that gives you the oil volumetric flow rate. Multiply that oil volumetric flow rate by the oil density to get the mass flow rate, and then work out the required pipe diameter for a given pressure differential. So how does this work? Reynolds number to Darcy friction factor to pressure drop, fluid mechanics. So we consider pipe entrance, exit, bends, pipe contractions, expansions. For different sizes in series, feed the outlet pressure from one section of pipework into the inlet pressure of the second section and do another iterative calculation. And this is how we would go about sizing oil lines.
I told you
things to consider. For transcritical CO2 with oil separator, oil retention concentration is 0.8% according to experimental data from published reports. So oil viscosity, we're not dealing with oil alone. We're dealing with an oil refrigerant mix, say 12.5% weight on weight concentration of refrigerant in oil. That reduces viscosity significantly from 240 pascal seconds to 74. at those conditions shown there. Reduced viscosity obviously makes that pipe sizing less stringent. We can use smaller diameters as a result of having that refrigerant in the oil. Again, I've given some sources there as to where I've got that from. And the link between refrigerant weight and weight concentration and viscosity reduction factor was also found in a report. I can give you all of those references. Consider the effect of actual connection sizes on the oil separator. Just because your calcs say that this is optimal doesn't mean that that's what the component will have. So you might have the effect of some reducers, etc. And that's important to consider as well. So this is a bit of a change in direction now. We're going to talk about part load system operations. So at part loads, we have lower volumetric flow rates, velocities, and therefore turbulence. Oil separators must keep their efficacy at lower loads and ambient conditions. When sizing them, think about the full range of loads and temperatures that could potentially be experienced and make sure that the oil separator is effective at that full range. Compressor turn down versus heat exchanger and pipe work minimum velocities are also important. So, for instance, brazed plate heat exchangers can typically get down to somewhere between 20 and 45% part load based on application and still return oil. So, sweat, for instance, stipulate a minimum channel velocity of 0.3 meters a second for MT applications to ensure oil return in their heat exchangers. And they then caveat that low temperature applications may require higher channel velocities, and that makes sense. So Alfa Laval go at it a different way. They actually are not so strict on the minimum channel velocity, 0.1 instead of 0.3 meters a second, but they expect a minimum channel pressure drop of 4.1 kilopascals at the same time as that 0.1 meters a second to guarantee oil return. So slightly different ways of defining expectations. Control strategies for ensuring oil return. So split heat exchangers. Instead of just having one big evaporator, can we split into multiple smaller evaporators that can be isolated during part load conditions to prevent the risk of oil logging? Individual oil management systems per compressor. So this helps match oil return to oil expelled from each compressor during operation. Variable speed drives to match compressor displacement to load also assist with oil return as well. And periodic oil balancing, which is where basically we run a compressor hard for a short period of time to basically equalize, to get oil back to all the compressors and get the levels right back where it matters again. So there are lots of different strategies at hand here for making sure that we get oil back to the compressors. So practicalities of oil: store it in a dry, non-corrosive environment prior to usage. Oil containers that are open should only be exposed to air for very short times. Open containers provide risks to particulates entering the oil, such as metals. Oil is hygroscopic and will absorb moisture from the air, which contaminates it and risks moisture being introduced to a system. And obviously, moisture and moisture-rich oil can react with CO2, forming acid within the system, which can lead to internal corrosion and alter the properties of the refrigerant during the refrigeration cycle, and we definitely don't want that. So this is a bit of a comparison of POE versus PAG. So POE is polyol ester and PAG is polyalkylene glycol. So moisture criticality, POE is better for that. High lubrication performance, PAG is better for that. In terms of solubility, miscibility, they're equal. They can be made to be equal. High temperature compatibility, PAG, is better for that, as we discussed regarding the Copeland transcritical scroll compressors. And we typically find that POE is used on hermetic and semi-hermetic applications, and PAG is used on open drive applications. So which to use? really depends on what you're doing, as you can see from this chart. And that's it, guys.
Yeah, that's a lot. You can stop. We'll just kill this share here. Nabil, that was awesome. That's a crash course in oil design. And even there, we went through that multiple times in our design course, and I've picked up a few things there. Oil carryover rate is one thing that you can run into major issues if you don't understanding. Temperature of oil, it'll affect the design, affect the oil when you're designing these systems. And it's super key to dive into that. So Nabil, thank you for sharing your expertise with us. We got a few questions in there. Please keep them coming.
It's a pleasure, Trevor. It's a pleasure.
So we got a question here. PDFs, I'll get out the PDFs to everybody. If you take our advanced design course, we'll go through that in more detail for sure. But you'll get all that. Would that be a critical charge system? So I think that question from Andrew was from the natural gravity system. No, that is not a critically charged system. I don't believe it. But I will double check. I will have to double check on that specific system that I've seen. But I've seen in a market store, and this was our NEG Canada unit, they used just a header, an oil header, and there was no reservoir separator. So, and we can dive into that. So that one wasn't a critically charged system for sure. The one that I was talking about with the big vessel, like Nabil was talking about, and then it has a drop down, all the oil goes down there. There was another question here. Can you give some examples of sign? Patrick, thank you for shooting some answers out. If you have some signs of catastrophic oil issues, some signs could be compressor amp draw, difference due to poor lubrication internals, great high temperatures. Yeah. So like Nabil said, if you get a really high temperature, it changes the viscosity of the oil. That oil separator cannot separate the oil from the refrigerant, which leads oil out into the system. And then, like Nabil said, there's oil in the evaporators, coating the coils, losing efficiency, losing cooling. Great questions.
It's a great question. And Patrick Gregory's answer is really good. Yeah, things you'll see, your discharge temperature will be higher than anticipated for the compression ratio, the pressures, the superheat, and the isentropic efficiency of the compressor. If it's beyond that, it probably means there's some issue with oil, usually. If the amperage is higher than expected, issues with oil potentially as well. That's a good answer, actually. But before that, you should be seeing it with alarms, really. You should be able to see it with low oil level alarms. You should be able to see it possibly visibly in terms of sight glasses on oil reservoirs, sight glasses on oil management sections, all sorts of things. So hopefully it doesn't get to that stage.
Yeah, exactly. Great questions. Once again, Once again, in the chat, if you want to book a call when we learn about the design course, do that. Nabil, how can people find out more about you, more about your organization, to really learn more how you can help them?
Go to our website, which is www.amiga-solutions.co.uk. Look at our LinkedIn page, which is Amiga Net Zero Solutions. Connect with me on LinkedIn, send me an email. It'd be a pleasure to speak to you.
I love it. Nabil, thank you so much for sharing your time with us here at CO2 Experts Live. And I look forward to seeing everyone here that's on the call next week. We're going to be doing this again and again and again to grow our knowledge together so we all uplift the industry. Once again, my name is Trevor Matthews. Always, let's get a conversation going. See you, everyone.